Hello, everyone. My name is Aaron Standard. I'm the founder and CEO of Petabridge, and today we're going to talk about something a little bit different. Normally on this channel, we talk a lot about Akka.net and building distributed systems that are event-driven, but today we're going to talk about a general software architecture practice that I've been in the habit of over the past 10 years, and I call it high optionality programming. And these are a series of techniques that are designed to help reduce the accumulation of technical debt over the lifespan of a software project. So the first video is going to introduce the concepts around high optionality programming, and the second video I'm doing in this series will talk about some of these specific software techniques you can use to implement it. That way we can keep each video relatively brief. So technical debt is a fantastic concept, and I went ahead and borrowed this cartoon here, and I'll link to that in the description to kind of help illustrate it. But the idea is that as you start making choices early on in a software project, the consequences of those choices get priced in over and over again as you keep building on top of those previous decisions, until you end up with a whole bunch of weight that's all sitting on top of those fundamental decisions you made very early on in a project. So to kind of illustrate this a little bit more clearly from a programming standpoint, imagine we have our historical data and our stakeholder expectations around how a system works. These are essentially the technical debt from the point of view of the end users. The technical debt exists both in terms of all the historical data that's been accumulated. That data has to be preserved and protected because that fundamentally is your business. And then on top of it, all of the user experience expectations your stakeholders have, like this feature should work this way, all get priced in around the way they start learning how to use the software. And when you want to significantly change how it works, you're going to have to retrain those users if their expectations change. So this is sort of the top layer of all your technical debt, is this historical data and stakeholder expectations. Now let's go ahead and zoom down to the bottom layer of our software, which is our choice of database in this case. So let's say we've built our entire application on the backs of a relational database like SQL Server. We've built up a number of different tables which store this historical data. We have lots of views and stored procedures that are modeled on top of it. We have reports that are used by business analysts to run key processes inside our company. We have an object relational mapper that our UI and application layers use to transform data transfer objects back into rows inside SQL. And then finally, we have user interfaces and then business processes. And then again, this top layer of historical data and end user expectations all built on top of that. So what technical debt fundamentally is that in order for us to make a change at a low level in our software, we have to essentially pay for the cost of propagating all those changes back up all the way to the end user's expectations. And depending on how you design your system, this can become prohibitively expensive. So what technical debt fundamentally is that you have some initial technical debt you incur as a result of your original greenfield implementation. This can be things like the choice of runtime that you're on, or it could be the choice of architecture or the choice of database. It really depends on how you do it, which is the entire reason why we are making this video. And that interest compounds in the form of layering. Every single time someone builds a new layer on top of those original set of choices, changing that original set of choices gets that much more expensive. And so the full cost of technical debt isn't going to be well understood until a future need to modify the system arrives. So let's say, for instance, SQL Server is now at such a large scale inside your system that you actually can't scale it up vertically anymore. And you have to look at a horizontal scaling solution, which means re-architecting your entire data model. Well, you're not going to necessarily know or understand what the full cost of that looks like in the future when you're designing a software system for today. And so the full cost of technical debt inside any given implementation really isn't understood until someone is tasked with trying to change it, at which point they have to create a work back plan and try to sum up all the different processes and essentially unknown costs that have been layered on top of the system over a long period of time. So the cost to make those changes at those low levels inside your software, whether it's doing things like moving to a new hosting environment, changing the runtime that you're on, rewriting the system in a new programming language, if you were crazy enough to do that, or possibly changing something like the database. All of those costs are the real technical debt at the end of the day. That's the serviceable debt you have to pay down in order to complete those changes. On the opposite end of the spectrum from technical debt is you have what's known as optionality. Optionality originally is essentially it's a financial concept which is that you purchase an option that you have the right to exercise at some point in the future. So a good example, if I wanted to go ahead and buy a stock option off of, let's say, E-Trade or any other stock trading platform, I could say I want to be able to purchase the right to buy Cloudflare, which is, publicly traded tech company stock, at $40 a share, and I have to buy, and options are usually priced in blocks of 100. So I have the right to buy 100 shares of Cloudflare at $40, and that option is good until, let's say, January 1st, 2023. So that option expires about 6 months in the future from when I'm making this video. And so you have to pay a premium in order to have that option. And what that gives you the ability to do is have some leverage that you can execute whenever you want. Let's say if the price of Cloudflare crashes, you don't lose all of the money that it would have cost to go ahead and buy those shares outright in June. So that's where the leverage comes from. Likewise, if there's a tremendous amount of upside and Cloudflare's share price shoots past our original strike price on our option, we make a significant profit without having to put in the same amount of input that we had before. That's sort of what financial options look like. In technology, the way options work is we basically have, let's say, different spheres of, let's say, sort of technical debt. A greenfield project that has no users and really doesn't have a lot of concrete sort of definitions or end user expectations already defined has a tremendous number of options because by its very definition, it's brand new. No one's using it. So there hasn't been any accumulation of technical debt yet. Whereas a critical product sitting at the middle of this diagram, let's say this is a critical product responsible for generating hundreds of millions of dollars of revenue a year for your business. That product's going to have the fewest number of possible options to change it in some meaningful way because it already has critical business processes that depend on it, end user data that we have to manage, maybe it has integration with other business partners, and maybe there's lots of internal processes within your company that all depend on this product working in a very specific way. In order to make any type of change to that product, you have to reason about all of those different pieces of weight that are sitting on top of it and try to find a way to make your technical debt pay off without having any adverse side effects on those. This greatly limits your degrees of freedom and therefore your options. Whereas products with fewer users or products that are earlier in the adoption cycle, for instance, a beta product, tend to have a much larger number of options. So this is the right mental framework to kind of think about how optionality works in technology. The earlier you are in a project's life cycle, the more options you have and the less expensive they are then. So here's the idea behind high optionality development. When options are cheap during greenfield project development, we can pay a premium designed to make it less expensive to be able to change things out when our product is successful later. Essentially, it's planning to succeed. In the context of startups, a lot of people tend to think in terms of minimum viable products, and they tend to essentially not pay premiums for having options to go ahead and modify and develop a product. And that's probably the right strategy for a lot of businesses. However, if you're planning on making a significant investment into a project and you want it to succeed over the long term, you probably should think about what are some low-cost ways I can build a lot of optionality into this product now to avoid having to pay a lot of money in the future later when I know it's probably going to evolve and change. It's almost a certainty that software will grow in both size and complexity over a long period of time. Therefore, we should try to pay a premium when it's cheap in order to do that. So what technical debt really is, reframing it in terms of high optionality programming, is technical debt is really the destruction of options is what it is. Technical debt occurs when you fail to anticipate how your software is going to evolve. And a really classic example of this is database-driven development, where you couple the way your software works to, well, let's say highly couple the way your software works to a very specific database implementation. And when that implementation no longer suits the way your application is used or the way it needs to be used, now you're in trouble. And you haven't given yourselves a lot of options to be able to migrate or take other types of actions, such as maybe moving part of your system over to a different database that's better suited for it, because everything is so tightly coupled together. So Yeah, and exactly. These are a couple of questions that tend to come up when the subject of switching databases is raised. By the way, Code Opinion made a very great video about this recently, and I'm going to go ahead and link to it here. You should definitely go ahead and give that a look if you want to learn more about the subject of who needs to migrate databases and how should you think about coupling to a database. He answers those questions very well. But the big idea behind high optionality programming is that future technical debt can be reduced by just taking the time to plan for future changes today. That's one of the things we can anticipate as software developers, and we can try to find ways to mitigate some of those problems before they happen, rather than letting it be a giant production crisis at some point in the future. So to help illustrate the high optionality programming concept, I want to do a case study. It's my business, my first company I started prior to Petabridge, and we're going to deal with the low optionality experience we had when we were first getting started versus the high optionality one we had when the company shut down. So let's go ahead and talk a bit about what those looked like. So Marked Up Analytics was fundamentally a real-time analytics startup. We built SDKs and a real-time dashboard for people who are building applications for the Windows Store on both Windows Phone and on the Windows 8 Store that was launching in 2012. And one of the things we did to differentiate ourselves from our competitors was we offer the ability to get real-time insights on how your application was being used, which is something that none of our competitors in the space could do. They all kind of worked around batch-oriented programming models. This is back 10 years ago, so this was kind of a pretty big point of differentiation back then. We originally built this software on top of RavenDB and Raven's MapReduce indices, which worked very well when we were doing an early proof of concept. We were able to get all the different time series data we wanted. We could even perform more complex queries, such as being able to determine the number of unique users over an arbitrary date range. For a significantly large data set, that's actually a pretty complicated problem. But RavenDB was able to handle that very beautifully early on. But after we had launched the service and started getting users to install our SDK, and as those apps started getting approved and distributed in the Windows Store, we had a period around Christmas 2012 where our traffic went from about 10,000 events per day, which Raven could handle no problem, to 5 to 8 million events per day. And all this growth occurred over a 3-day period. And RavenDB absolutely died right around the point we hit a couple million events per day. And the biggest issue we had with it was those MapReduce indices would stay stale for several days at a time. We had to continuously migrate data from one RavenDB instance to another in order to make sure the newest data got populated into those indices first, and all the historical data would get added later. And so we had to constantly transfer data around between these databases in order to get it to work. Replication wouldn't work either. We had issues where we tried sharding the system and replicating it, and we noticed that Raven would lose about 40% of events when we did that. So it was a pretty terrible experience. And bear in mind, this is all happening right as my personal money I was using to fund the company was running out, and we were starting to raise capital from investors. So this was a pretty stressful time for me. Now, the decisions we made that made this really difficult for us to change, originally we basically decided to do a quick and dirty minimum viable concept because we had no idea what the success rate of the Windows Store was going to be like. It was a totally new market. We had no idea what it would be like for us as a new entrant in the analytics space to get adoption. And we had no idea what the app developers themselves are going to end up adopting. So we decided to go ahead and use very inexpensive development techniques to try to get something out to market quickly. One of those was, and this was actually advocated by Allende, the creator of RavenDB, was to avoid the repository pattern and just include database logic directly inside our controllers and other parts of our application code responsible for doing things like totaling and aggregation. And so as a result, we had database logic spread out everywhere throughout our system. And this turned out to be a catastrophically bad decision for us. Because once we came to the conclusion that Raven was fundamentally the problem and there wasn't any fix for it, the engineering quality around it at the time was so poor that we couldn't trust its built-in tools. It wasn't able to take advantage of even very highly provisioned machines. We had, at one point, a machine with 64 cores, and Raven couldn't even basically use all of that to keep up with a relatively low amount of traffic, in my opinion. 5 to 8 million events per day is not very much. By the end of Marked Up's lifecycle, we were doing well over 100 million events per day using a large Cassandra cluster that we ultimately migrated to. But the real problem from an optionality standpoint was because everything was not abstracted, it was all baked directly into our business logic, it was very difficult for us to extricate ourselves from RavenDB. as everything in our software was highly dependent on RavenDB specific constructs. So of the original capital that we raised, we probably spent a couple $100,000 of it, which is about 25-30% of the money that we raised, just funding the cost of trying to migrate onto a more sustainable infrastructure we could use. And we did that instead of working on things that would actually grow our bottom line and grow the business. So we paid quite literally a pretty high price for this. Now, one of the things we did differently in the next iteration of the software, having learned from our mistakes the first time around, is we decided to architect everything in a very event-driven sort of model, that which we didn't have. We didn't have such a robust concept of that before. It was mostly kind of like API and RPC driven. We decided to move to an event-driven architecture. And so we would go ahead and have an event come into our system, and we created a piece of middleware that could translate each event into essentially some analytic deltas, meaning increment this counter, increment that counter, increment that counter, where we would pre-compute not the absolute values of what each analytic event would have on the overall totals for that application, but rather we could compute the size of the change. And we separated our read and write models into two different discrete services. So we had a in analytic systems, for every read your system has, you probably have 20 to 50,000 writes. That's just sort of how it pans out when you're at scale. So we had a very aggressive set of definitions around our read side, designed to make reads instantaneous, since we're trying to build a real-time analytics system. So it was essentially grabbing a whole bunch of time series data and then backfilling wherever we had gaps. And then our write models were all about transforming these batches of events into analytic deltas and computing them as quickly as we could. And so a couple of the things that really helped us achieve some success here was that by being able to go ahead and abstract away some of our infrastructure, we're able to effectively restore unit tests around our application. Everything we had before in our previous iteration of Marked was all integration tests because everything was so tightly coupled to Raven. Well, now that we had this sort of middleware that was ultimately going to point to Apache Cassandra, that was our sort of data store of choice for being able to scale this application horizontally, we were able to go ahead and test what the output looked like from that middleware without actually having a database around at all. So we're able to go ahead and just make sure the deltas were what they should have been. We didn't necessarily care what the totals were coming out of the database, since that's a read side problem. We only cared about write side computations there. So being able to add unit tests back to the suite was a huge benefit for us, and it ultimately really helped improve our development cycle time a lot. Next was we're able to, when we introduced our second product, which was real-time marketing automation, this is the one that we had hoped would be a big moneymaker for us, was we created a DSL that allowed dynamic filtering, a user-defined filtering of events. And this could be used for being able to do behavioral targeting of users who are using your application in the Windows Store. That DSL was very flexible by design, and we essentially built it with a lot of optionality to be able to support new dimensions that didn't even exist yet. And, I could have bought into the idea that maybe we should just have some pre-baked rules and a rules engine that can just kind of slap them together. And we actually tried to build a V1 that way first. But I decided that building something that was fairly future-proof and extensible, and also could be, essentially it was like Turing complete is probably not the right word, but we're able to go ahead and verify which rule sets were valid and which ones weren't using a abstract syntax tree compiler that I wrote. This DSL was going to give us a lot of future-proofing and make it really easy for us to support all sorts of new complex campaigns in the future that we couldn't support today. And then this ultimately greatly improved our developer throughput. So a couple of the other things we did with Marked Up in the second iteration that really helped improve our performance was the separated read and write models usually meant we had a repository style abstraction around a feature area. So these weren't generic repositories that touched everything. It was more like we had a repository for being able to get time series queries that touch this data. We had a separate repository for getting access to billing information. And then we had a repository for some really sophisticated queries, such as, I mentioned earlier, the number of unique users over an arbitrary time range. Well, some of our applications had as many as 1 million daily active users. Being able to figure out of those over 30 days, how many of those users were actually unique could be quite an expensive problem. And as it turned out, we needed to migrate off of Cassandra and onto essentially a Solr index built on top of it in order to efficiently compute that. And that's exactly what we did. And by having those, let's say, abstractions in place there, it was very cheap for us to change that on the back end without having to necessarily update our front end. So we had a sufficiently strong layer of abstraction now to make it easy to introduce those changes. And the really core tenet that brought all this together was that we knew we were going to probably have to make those changes in the future. So we decided, while we're undergoing this painful refactoring of our existing system, let's pay the premium to do that now. So it's easier for us to do that in the future, and it's not going to be another giant six-figure project the way those older ones were. We can't afford to do those every year. And so this strategy worked very well for us. And since then, we've been able to go ahead and reuse these strategies and tactics with hundreds of customers here at Petabridge over the years. So the next thing I'm going to go ahead and touch on real briefly, I'm just going to give you a preview of what we're going to lead into in the second video in this series, which is all about how to actually implement high optionality programming. And here's an example of some of the techniques that you can use. The first one, which I've already mentioned, is event-driven programming. That gives you a lot more flexibility than RPC does. Event sourcing is another good one. CQRS, and specifically being able to go and separate your read and write models from each other, that gives you a lot of flexibility that you might find very valuable in the future. We certainly did at Marked Up. Actors are another good one. They give you the ability to go ahead and simulate new behavior on top of old data, which is very, very useful. And then moreover, we're going to talk a bit about extend-only design. Now, I've just recently done a video on this subject, talking about how to version Akka.persistence events and states using this technique. If you're interested in learning more about that, I recommend giving that a watch. But otherwise, thank you very much for watching. If you're interested in having Petabridge help you and your organization learn how to achieve high optionality programming, please go ahead and click on the link at the very bottom of the description. Thank you very much for your time, and I'll look for you at video number 2.